Let us now consider practical problems considering the topic. Let us have integral by surface omega of 2x minus z dy dz plus 3z dx dz plus x plus 2z dx dy. And omega is outer side of x plus 4y plus z equals 4, x, y, z is greater or equal 0. So we will have x is z, x and y. We have x plus 4y plus z equals 4. So if y and z are 0, then x is 4. If x and z are 0, then 4y is 4, so y is 1. And if x, y are 0, then z is 4. So you'll have something like that. This will be our triangle, and upper part will be that side. So, to calculate this integral, we have to determine if this surface is definitely projected on, for example, xy. Definitely it means that each point of surface corresponds to one point of projection. Here it is definite. To calculate this integral, we can use next formula, integral of second kind of a n 0 d sigma is double integral by projection by xy a n 0 divided by modulo of cosinus gamma, where z is substituted by its function dx dy. This z is derived from the equation of the surface. Now we have to calculate normal vector. But as we know from linear algebra and geometry, these three numbers will be coordinates for the normal vector. So vector n will have coordinates 1, 4, 1, and its module, its length, will be square root of 1 square plus 4 square plus 1 square will be square root of 18. And so n0 will be n over absolute value of n, will be 1 over 3 square roots of 2, or square root of 18, which is the same, plus 4 over, not plus, other coordinate will be 4 over 3 square root of 2, and 1 over 3 square roots of 2. So this will be cosinus gamma, because as we remember, this is cosinus alpha, cosinus beta, cosinus gamma. And vector function a can be taken from initial problem. This is 2x minus z, 3z, x plus 2z. Scalar multiplication of a by n0 will give us 2x minus z plus 12z plus x plus 2z divided by 3 square root of 2, which will be 3x plus 13z over 3 square roots of 2. Here we multiply each coordinate of a by each coordinate of n0. We multiply first coordinates, second coordinates, third coordinates, and then add them, the results. And we get this expression. From equation of the triangle, we have that z is 4 minus x minus 4y from equation of our surface. So a n0 divided by cosinus gamma and substituted with z equals 4 minus x minus 4y will be, if we divide this part by cosinus gamma, which is 1 over 3 square roots of 2, we'll get just 3x plus 13z with z equals 4 minus x minus 4y, and if we substitute this in, we get 52 minus 10x minus 52y. Now finally we can write down that this integral by omega 2x minus z dy dz plus 3dz dx dz plus x plus 2z dx dy will be double integral by region d oxy 52 minus 10x minus 52y dx dy. So if we draw this projection on x, y, we have x plus 4, y plus z equals 4. So here we have z equals 4, so we have x plus 4, y equals 4 remaining. Now if x is 0, then y is 1. If y is 0, then x is 4. So we'll have a triangle from 1 to 4. This will be our region D, O, X, Y. So we will have integral. Let us take outer part by y will be from 0 to 1 dy. Inner part will be from 0 to 4 minus 4y. Because if we express x here, we'll get 4 minus 4y. Now, here we just substitute 52 minus 10x minus 52y dx dy, and if we calculate this integral, we'll get 188 over 3. Let's consider one more problem. We have integral by omega second kind by surface 5x squared plus 5y squared plus z squared dx dy, where omega is outer part of hemisphere. Z equals square root 4 minus x squared minus y squared, and this hemisphere is cut out by the cone z equals x squared plus y squared. So we have a hemisphere and we have a cone cutting apart from it. We'll get something like that. If we have only one part of this integral, so actually this will be something like a equals 5x squared plus 5y squared plus z squared 0 0. So we can use formula integral by omega r of x y z dx dy equals plus minus depending on outer or inner part of the surface doxy r xy z of xy dx dy. So we just transform this integral into double integral by the projection. Now we have to find this projection, but to find it we have to know what this line is. This line is a circle, but how to find it? Its equation. We just have to write down equations of two surfaces into a system. So if we solve this, we get square root of x squared plus y squared equals square root of 4 minus x squared minus y squared. If we make a square out left part, we get x squared plus y squared equals 4 minus x squared minus y squared. So we move this part to the left, we get 2x squared plus 2y squared equals 4. So x squared plus y squared equals 2 will be the equation of this line. Now we know the equation of the circle that our surface projects into. So let's calculate it. We'll have outer part of the sphere, so plus double integral dOxy 5x squared plus 5y squared plus 4 minus x squared minus y squared, substitute z, dx dy, we can simplify it a little bit, we'll get 4 dOxy, and we'll have 1 plus x squared plus y squared, dx dy. Because this is a circle, we can transform to polar coordinates, so we'll get 4 integrals by d with wave, 1 plus rho square by Jacobi determinant rho by d phi by d rho. Now when we calculate this, we get 4 integral minus pi to pi d phi, integral from 0 to square root of 2, 1 plus rho square d by rho by d rho, which will give us 4 by 2 pi by rho square over 2 plus rho power 4 over 4 from 0 to square root of 2, and in the end we get 16 pi. Next example. We have integral by omega z square dx dy, where omega is outer part of the hemisphere, y equals square root of r square minus x square minus z square, where r is a real number. If we draw a picture of these surfaces, we'll get something like this. Now, we have an integral that, if we use formula specified in previous problem, we will get non-definite projection, because this part will be projected on the OX and this point will also be projected into the same point. So we have to split this sphere, this hemisphere, into two pieces, into upper one and lower one, and these two pieces will be projected definitely in one region. So we'll have integral by omega z squared dx dy equals integral by omega 1 z squared dx dy plus integral by omega 2 z squared dx dy. Now we'll have a projection. Well, our sphere will be projected into circle, and the circle will have an equation x squared plus y squared equals r squared, and y will be positive because it's only a right hemisphere. And this vector forms positive angle with the OX, and this vector forms negative angle with OX, OY, with coordinate axis. So integral by omega 1 z squared dx dy will be plus integral by d r squared minus x squared minus y squared dx dy, and integral by omega 2 z squared dx dy will be minus integral by d r squared minus x squared minus y squared dx dy, and these two integrals will provide us with same value but with different signs, so this integral will be 0. One more problem. We have to calculate integral, double integral by omega of a n 0 d sigma, where a is xi plus yg plus zk, and omega is x squared plus y squared equals a squared. So this surface is a cylinder. Because we have fixed x and y, they form a circle, but z is not fixed. So this will be cylinder. Now, as in previous case, we cannot project this surface onto one plane explicitly. Why? Because if we try to project everything OXY, we will get a lot of points projection on OXY. But if we project everything, for example, on ZX, we'll have only 2 points projecting into the same point. So now we can split this cylinder into 2 pieces where y is positive, y is negative, and calculate both sides. So here we will have integral of a and 0. This sigma also will consist of 2 integrals. Let us calculate each of these integrals. First one, a and 0, d sigma will be calculated as double integral by projection by x z a and 1 0 divided by cosinus beta absolute value, where y equals y of x z dx dz. So we divide on the angle that we are omitting. So here we are getting rid of y, and that's why we substitute everything with y, and we divide this multiplication, this product, by absolute value of cosinus beta. Now we have on omega 1 equation y equals square root a square minus x square. So f of x, y, z equals x square plus y square minus a square equals 0 is the equation of our surface. Now we have to use gradient to find our normal vector for this part. So n1 will be plus gradient f or 2x 2y 0. n2 will be minus gradient f will be minus 2x 2y 0. Now absolute value of n1 will be same as absolute value of our n2 and will be square root of 4x squared plus 4y squared. So n1 0 will be x over square root x squared plus y squared, y over square root x squared plus y squared, 0. And this will be our cosinus beta that we require. Now a n1 0 scalar product will be x, y, z, our vector function, by x over square root x squared plus y squared, y over square root x squared plus y squared, 0, and we will get x squared plus y squared over square root x squared plus y squared, which will give us square root x squared plus y squared in the end. And a n1 0 divided by absolute value cosinus beta with y equals square root a squared minus x squared will be x squared plus y squared over y, where we substitute a squared minus x squared and we get a squared over square root a squared minus x squared. And finally, integral by first part, a n1 0 d sigma will be a square integral by projection doxz a square dx dz over square root a square minus x square, and we get a square integral from 0 to a dz integral from minus a to a dx over square root a square minus x square. Why? Because the projection of this cylinder on xz is just a rectangle. So we calculate integral by this rectangle and we get a square by a by arc sinus x over a from minus a to a, which will give us ba cube. Integral by omega 2 of a n to 0 d sigma will actually be the same. Why? Because we have y equals minus square root a square minus x square, negative part of the cylinder, and normal vector will be minus 2x to y 0. So these two minuses will compensate each other and we get the same ba cube. So our integral by omega a n d sigma will be 2ba cube. This will be the answer. One more problem. We have vector field 2xi plus 2yg plus minus zk. And this flows is going through outer part of closed surface. Omega specified by z equals x square plus y square, square root of x square plus y square, where z is from 0 to h. And we have to find the flow of liquid through this surface. So flow of liquid is integral of second kind by surface omega a n 0 d sigma. And we have a cone specified by this equation, and it's closed on the top by a head on the level h. Now here we have a surface that surrounds some body, so we can use Gauss Theorem. Here we can just take integral by g dp by dx plus dq by dy plus dr by dz dx dy dz. So we will have triple integral by g dp by dx is 2 plus dq by dy is 2, dr by dz is minus 1, dx dy dz equals 3 integrals by g dx dy dz. Now triple integral by body g dx dy dz, nothing here, just 1. So this integral equals to the volume, and volume of such a cone will be 1 over 3 by ph square by h, which will give us ph cube. This will be the flow of the field.